So leading off here, we have a good friend, Bert Bennett from ICM.
All right, large-scale biomass gasification and the co-production of biochar and bioenergy. The idea and the focus of this talk is to have a bit of an eye on large-scale climate solutions and considering viable options that are, in my view, practical. The one pathway that I'll be talking about is biochar and CHP systems, where we're looking at co-production of high volumes of biomass, biochar, and then the co-production of a carbon-neutral combined heat and power. So large scale, for me, the large scale is equivalent to one of our dual M-300 configurations, which is able to take in about 600 metric tons per day of woody biomass, co-produce up to 100 metric tons of biochar and 18 megawatts of electrical power. Where would we want to locate these? Not in my backyard, obviously. We would probably think about upgrading existing or decommissioned power plants or industrial forest product processing facilities, locate near medium to large municipalities, or look at reducing carbon intensity around cement plants and biorefineries. One of the things I wanted to compare, I'm a gasification guy, and I wanted to see how well we would compare with pyrolysis as far as an overall impact on climate. The way I did this, by using some pretty powerful simulation software to model up combustion processes around a combined heat and power components that include biomass dryers, gasification or pyrolysis, heat recovery, steam generators, steam turbines, and basically for both approaches, we looked at the identical feedstock inputs, and biochar yields are based on pyrolysis of close to 28% dry matter yield, with approximately 100% of all the recalcitrant carbon in the feedstock going to the biochar. The gasification system, we looked at about 22% yields, with less than 100%, 92% of the recalcitrant carbon going into the biochar. And the maximum recalcitrant carbon that we have available to us is based on the fixed carbon that you would get from your feedstock analysis, proximate analysis numbers. The comparison was made on a single very cold day and also included drying about 1,000 tons of wet feedstock down to 15% moisture, 600 tons a day of dried feedstock. And the leftover low-grade heat, we just included that going to some local industrial greenhouses to take that heat on those very cold days. So I'll give you the results first. And the gasification system has a greater capacity to provide combined heat and power. In this particular model, we had double the amount of net electrical power going to the grid, close to 16 megawatts versus close to 7 for the pyrolysis-based system. Both systems were able to generate enough waste heat to dry the 1,000 tons down to the 600 tons of dried feedstock. And then we had about 3 times as much waste heat available to heat a greenhouse, equivalent of about 5.4 hectares of greenhouse versus 1.6 for the pyrolysis-based system. So why is that? It's pretty simple, really. The gasification process is based on direct fired autothermic process, where we're basically running an exothermic process that generates enough heat to drive off the volatile matter and partially oxidize it and sustain that gasification process. Whereas indirectly heated pyrolysis systems, they'll take their gases and combust them and then use part of that heat to run their reactor. And as a result, there's just not as much energy available to a post-combined heat and power application. If we just look at biochar, the pyrolysis guys were able to gain more yields, largely because they were putting in more volatile matter into their product. But if you just look at the amount of available recalcitrant carbon that we had going into the biochars, the difference between the pyrolysis system and the gasification systems were not that great. So taking a little closer around the CO2 removal and fossil carbon offsets. If we look at the combined heat and power and the biochar's removal potentials, and only accounting for the recalcitrant carbon going into an agricultural soil, the results showed a somewhat similar tons per day, but the gasification-based system was able to put out more into the offset and removal, and that really was a function of a greater capacity to generate electrical power. Also wanted to talk a little bit about permanent storage. By no means am I advocating taking the good stuff and taking away from agricultural soils, but there is an enormous reservoir of potential feedstock that are less than ideal for agriculture, especially around the municipalities. There's a whole bunch of carbon that could be captured, and maybe we'd want to put that into a hole or landfill covers, whatever, but there's a great potential of feedstocks that would be available. Just quickly, a little more on permanent storage. To pump a biochar slurry into an old abandoned mine takes a lot less capital and a lot less power than it does to compress CO2 and force it into a deep geological formation that would be able to hold back and keep CO2 sequestered. So when we start looking at the overall climate impacts of these high volatile matter biochars and sending it into a permanent storage, once again, gasification is able to slightly outperform the pyrolysis, not by much. We're talking about 8 to 10%, but once again, it all drives into that we're able to generate more electrical power than the pyrolysis system. Wanted to quickly take a touch on feedstock transportation. I know there's a lot of concern over long distance transport, so I just did the numbers real quick and assumed 50 trucks going into this facility, about 5,000 total miles a day, and looking at the amount of diesel that we would use. Basically, we're talking about 9 metric tons of carbon going to the fossil fuel versus about 500 metric tons that this facility could generate and offset. And then that doesn't, of course, account for harvesting wood and pulling it off the mountain, et cetera, but the actual transport is not that much. And if you start transporting biochar, at the end of the day, there's still plenty of removal capability to offset those transport costs. I wanted to share some more details. I'm going to fly through these. It's more for the engineers that would like to dig into numbers after the conference. We looked at pyrolysis system performance, and we used a very reputable producer of pyrolysis reactors to get an estimate of how much waste energy is available for the CHP systems. We used that value. We used their yield values. They also indicated for some of their larger unit, they expected 120 kW power load. We assumed about 60% of that in our overall parasitic load estimates. Here's process flows, gasification and pyrolysis, very similar. The big difference is that the pyrolysis system, it took a lot more units, and the thermal oxidizer combustion products have to go first through the reactor to transfer heat into the pyrolysis materials, and then it goes to the boiler system. For those interested, this is feedstock drying and low-grade heat that we were able to pull off that system. The mass and energy balances around the gasifiers and pyrolysis reactors. Once again, this will be available after the conference. Heat and steam turbines, mass and energy balance, the power and the low-grade heat that we had available to us. Feedstock characteristics. That the only thing here I'd point out is that the approximate analysis of this feedstock had about 20% of fixed carbon on a dry ash-free basis, and that set the limit of how much recalcitrant carbon I had going into the biochar. Whether that's the right approach, I can't say for sure, but that was how I handled it. Here is some just a general estimate on parasitic loads, gross power and net power production. The gasification system had a lower parasitic load than the pyrolysis system, not by much, about 600 or so kW. Had also two versions, one with the high moisture, cold ambient temperatures, and then with mild temperatures and about half the dryer load. Combined heat and power, these are usually, at least at the large scale, very proven, well-developed and mature technologies from feedstock receiving, hogs, low-temperature drying systems, storage, magnets, screeners. All these systems are well-developed and commercially available. For these large-scale systems, my preference is to stick with steam turbines, especially at the larger scale. There's enormous economies of scale associated with turbines. 5 megawatt unit could cost you $2 million, 20 megawatt, $4 million, and a 40 megawatt, $6 million. So there is quite a benefit to economy scales. Air-cooled condensing systems and low-temperature dryers work very well together. They integrate well, and they allow to capture low-rate heat from the turbines and run the dryer, and so there's significant OpEx benefit. Low-temperature dryers also have very significant reduction in emissions compared to high-temperature drum dryers, etc. Problem with the low-temp dryers, they usually cost more. Same problem with the air-cooled condensers. They cost more than traditional cooling towers, but they also have a benefit of eliminating a lot of water consumption typically associated with air-cooled cooling towers. We've been working with this technology for some time now. It was originally developed in the 70s. Since then, we've had it for 16 years. We've put a lot of effort in developing, refining, and demonstrating this platform. We've had a couple demonstration facilities. Tom has been out to a few of our facilities and greatly appreciated his input over the years. Lots of different feedstocks tested, a lot of biochar that we shared with the research institutions. And the key to our interest in this particular technology is its unique design. There's only one moving internal part, and which is the key to our ability to really provide a lot of control in the process. It's basically a horizontal flow gasifier. It's air-blown, autothermic, very low power draw, very good scalability, especially when comparing to indirect fire systems or traditional updraft and downdraft gasifiers. The better control scenario is all about the fine control we have over mass inputs, our ability to control speed, bed depths consistently, retention time throughout the unit, and probably the most important piece of that control is a zoned air input down the length of that unit that really gives us the ability to handle a lot of different feedstocks and maximize biochar, or go the other way and maximize energy output and minimize biochar. Our low power draw has a lot to do with the autothermic process, and also that it's a cross-flow gasifier. For example, our 300 ton per day unit has about a 70 kW draw. That's including in-feed and takeaway conveyors, feedstock metering, an internal auger drive that's only requires about 5 kW of power, and gasification air supply. After startup, no external feed is required. Fuel is required to keep it going. The autothermal process is the key to keeping that process going on a continuous basis. Our gasification biochars are typical. What you would expect to see from a 550 C to 600 C gasification biochar. Changing the theme a little bit, I also wanted to sort of compare gasification and highlight some of the importance around the way it oxidizes its combustion products and how it compares with biomass boilers. Regarding costs, we're pretty competitive, and that has a lot to do with our modular approach to the building components. We also, looking at the biomass boilers themselves, they're well-developed technologies. They're able to efficiently convert feedstocks into combustion products. But if you're looking to maximize biochar, that's not necessarily a big advantage. And of course, if that was the goal, we could easily design our gasifiers and thermal oxidizers to match those efficiencies. Biomass boilers are also able to combust very high moisture feedstock, but once again, if you're thinking about maximizing biochar, that's not really an advantage. Another important difference between our system and traditional biomass boilers, we collect all our biochars before going into a thermal oxidizer. Most of it's coming out the back of the gasifier, which would be a high carbon product, especially if you're using feedstocks with low ash content. We also get a low carbon, high ash product coming out of our knockout system. And then at that point, we go into our thermal oxidizer, and we maintain constant high temperatures throughout that process. In comparison, most biomass boilers collect a lot of their char at the feedstock, at the outlet of the boiler. There are some biomass boilers that can be designed to operate in the gasification mode, where they're pulling chars off of their grates. And there's some pretty slick approaches that sort of pull a stream of char out of the center. Their biomass boilers allow them to avoid some of the fly ash and get higher carbon yields. However, independent of that, they're all exposed to a higher emissions profile than what we would see at our gasification thermal oxidizer platform. And that's simply because we're able to provide a lot longer residence times at optimum temperatures for oxidation, whereas inside a traditional biomass boiler, you're quickly reducing your temperatures to below optimum, and residence times in the biomass boilers are significantly reduced compared to our long residence time thermal oxidizer. We can have 10 times more residence time at peak optimum temperatures, and even more if that's what required by the site. And at that constant high temperatures, during that whole time, we're at maximizing thermal oxidation. Because we're going up and down and around turn and lots of good mixing, we also improve the reaction, the combustion reactions. We also incorporate sort of standard design practice in thermal oxidizers for staged combustion that allow us to maximize oxidation and minimize thermal NOx formation. As far as NOx control, using traditional selective non-catalytic reduction methods, we have up to 20 times longer residence time than many biomass boilers at optimum SNCR temperatures, which typically range between 850 and 1,000 degrees centigrade. In a biomass boiler, those temperatures are quickly dropping as steam is being raised as the flue gas passes through those units. We've had a couple we have one dual M-300 system located in Kansas. It's co-generating 7 megawatts of electrical power, producing over 60,000 kilos an hour of a medium pressure plant that goes to an ethanol facility. We commissioned that unit in 2020. Since then, we've been commissioned and completed a preliminary engineering contract for a second dual system. This is a larger scaled system. It's the same dual M-300 system, but both gasifiers running at full capacity, close to 600 metric tons throughput, over 100 tons of biochar, and 18 megawatts of electrical power generation. Other potential applications that just wanted to quickly talk about, cement plants, looking at the fuel used to run the rotary kilns and the calciners. We're able to, we quickly looked at a offset of a portion of the fuel going into a calciner, and we were able to basically offset near 90% of the fossil fuel in the fuel used to run that cement plant. And of course, there was plenty of carbon left over that eventually, hopefully, can get into the cement mix or as an additive down the road when that becomes more readily accepted by the commercial market. MSW, we quickly looked at combining urban waste biomass, refuse-derived fuels, and biosolids. These chars wouldn't be something you'd want to put on your ag lands, but they would be something to place in a large hole somewhere. The interesting part is we were able to offset the fossil carbon contained in the plastics that are typically part of a refuse-derived MSW fuel, and offset that with the biogenic biochar. And then that left about 14 megawatts of electrical power, where we're offsetting a significant amount of carbon dioxide to that would typically be using either natural gas or petroleum control to be or coal to be generated. Quick, just another benefit here to add that none of this even considered some of the benefits of removing and reducing landfill methane by avoiding and minimizing the amount of urban biomass and RDF going into the landfills. We've also been doing some R&D work around fermentation, and we've developed a special reactor that's ideal for dilute gases coming from gasification processes. That's still not quite ready for prime time, but we're excited about the potentials of fermentation and also co-producing some valuable commodity chemicals at these larger facilities. So in conclusion, I just wanted to say that the large-scale gasification systems are proven, they're out there, they're commercially available. Large-scale balance of plant systems are also very well developed and mature technologies. The downside of these systems are generally very expensive, a lot of money involved to put them together. Challenging ROIs here in the US due to low energy costs. They take a couple years to get together. Municipal systems are further challenged by community concerns over emissions and odors. The one good news for the gasification platform is that we have a long residence thermal oxidizer that is not incineration. It has a lot better emission potential profiles than traditional incinerators. And so with that, thank you very much.
Biochar.org appreciates the support of our sponsors, exhibitors, presenters, and attendees. We look forward to seeing you at our next conference in September 2025.